What we're talking about today is the Bohr model, the Bohr model of the atom. We've been through the other models, and now we're going to talk about the Bohr model, and we've already talked about all the light theories, the emission and absorption, and the wavelength theories of light, and we're going to put this all together in the Bohr model. But what you need to do and put in your notes is the Bohr model number 1 was a planetary model. Planetary model for electrons. See, he was the first person to organize the atom in terms of arranging the electrons. Now, so if we have a nucleus that's positive, sometimes we'll call that a nuclear charge, what Bohr said is there were shells or there were orbits that went around the atom. And they went in circuit. Electrons traveled in these orbits that went around the atom. Now, very simply though, he not only said that there was an organization for electrons, he included that the ideas of Planck, I guess I should put a capital P, so he incorporated the quantum ideas of Planck, okay, I'll get that thinner, and Einstein. Now we talked about Planck's black body radiators, and we talked about Einstein's photoelectric effect. And these guys combined talked about the, well, specifically the idea that compounds or matter is quantized. And the idea that you're quantized means, and this is important, that the atoms or the matter they were dealing with had discrete energy levels. Meaning they could only absorb specific amounts of energy, nothing more, nothing less. Now, according to the Bohr model, okay, electrons' energy levels were specific to their proximity. Okay, so I always looked at for third one that the energy of these quantized states, or for electron, was based on proximity. How close were you to the nucleus? So proximity is a nice word that describes how close you are to something. For instance, if I have electrons that are existing, let's say in the first orbit, they have lower energy than electrons that can exist in, let's say, the third orbit. Let me continue drawing this. So this is the third orbit, and I'm just going to kind of leave the rest out, but this is the third orbit. So if I've got electrons in the third orbit, these electrons have higher energy. Now why? Well, very simply, electrons that are existing closer or closer to the nucleus are feeling the positive attractive force of the nucleus more than electrons that are existing farther away. So this is the first energy level. Being closer to the nucleus means electrons have lower energy. They're more being controlled, if you want to think of it that way, by the nucleus more because they're closer. Electrons that exist farther away have higher energy. All right, because they're able to exist farther away because they can overcome this attractive force somewhat. Now, we have some other words that are important. Electrons that start in their positions close to the nucleus, we call this the ground state. So the ground state is a way of saying you're grounded and that you are in your most stable position. We've already learned that stability means you have low energy. Why? If you've got low energy, you're going to stay in that state until you gain energy. So things that are stable stay in their positions unless given a lot of energy. Now, if electrons leap to a position that's farther away, we say because they now have higher energy and moved out of their stable position, they're unstable. Why? Because they have high energy. And anybody who has high energy, usually hyperactive, okay, there's just jumping around. You don't know what they're going to do. They're going to burn that energy off, so they're unstable. They're going to change at some point very quickly. And we call this state where people or electrons have high energy, we call this the excited state. People that are excitable or are excited have high energy, and they're going to do something. People on a sugar rush, okay, are going to do something. So to understand this, to go from a position closer to the nucleus that we call ground state, stable low energy, and jump to a higher state, what you have to understand is that energy is being absorbed. So energy is going into the system or the atom, but this is important. That energy isn't any old energy. It's quantized. It's specific. To go from this position where we're talking about the first shell to the third, we need a specific amount of energy. So we definitely have to absorb only that energy that gets me to this position. Now, once that electron is excited, in its excited state, what's it going to do? Well, it's going to do something. And what is it? It does, it jumps back to eventually to its original position. So it eventually gives off its energy in the form, okay, that it accepted. So it gives off a specific amount of energy when it jumps back from its what? High energy back to the low energy. Farther away back to closer. So energy is emitted, okay, given off when it goes from high energy farther away to close. And it's given off in the form of electromagnetic radiations. You'll hear the word spectra. You'll hear the word photons of light, which represent light acting as a particle with a specific amount of energy with it, or the word light. But again, all of this represents energy that is what? That is specific, which we called quantized energy. The atom is made up of specific energy levels. These energy levels are based on the proximity to the positive nucleus. So if the farther away we go, the electrons have higher energy. Electrons that exist closer have low. So if you got low energy and you want to go to high energy, the only way this leap occurs is if energy is absorbed. So electrons move away from the nucleus, become excited, unstable when they absorb energy. This is important. And of course, when they jump back from their high energy to low energy, they have to give off their energy, and they are emitting or releasing energy. Today we looked at the emission of light from gases being excited in their gas discharge tubes. And the light you saw was the energy given off when electrons jumped back to their original position. You saw that classic red line for hydrogen. That represents a jump from the third back to the second. Okay, so if this was, let's draw one more shell. If this was the, this is the third shell right here. So an electron jumping from this position back gives off a red line. And that color that's red represents low energy, because we learned that red color has less energy in its photon than, let's say, the green color that we talked about. The green has higher energy than the red. So we learned that the light that we see, those bright line spectrum that represent a group of the same photons building up on your diffracting lens, represents electrons jumping back. But you have to remember, it starts with electrons being absorbed. So let's see the whole story now. Going back to a nucleus, and I keep reiterating the same thing because it's so important. This is a nucleus. It's positive. It's not a neutron. It's positive. Okay, let's draw our shell. This is the first, second, third, fourth, and fifth. Okay, they're circular orbits. I'm just drawing part of them. Okay, if I've got an electron that's existing in the second, this is the first, second, third, fourth, and fifth. We call these shells if you want to. Okay, shells, or you can call them orbits. Okay, it's the planetary model. Now this negative electron in its ground state, meaning what? It's in its most stable position, okay, gains energy from electricity, okay, that goes through that black box. So electricity or energy gives this electron enough energy to overcome the positive pulling force. It jumps to the third. When it does so, it becomes excited. It's in an excited state. It doesn't last in this position very long. And what it does is, of course, very quickly, it jumps back. And when it does, it gives off that red line that we saw. This doesn't happen just once. It happens trillions upon trillions upon trillions of times per microsecond. So you get this buildup of red line. But that's a specific amount. We also saw a green line. Okay? The green line, if I can see here, is even what? Higher in energy. And that's from an electron that went from the second, jumped to the what? Fourth, because it what? Absorbed more energy. And when it leapt backwards, okay, it gave off that green color that we see. It was a bigger leap. It required more energy, but more importantly, it had to be an exact amount of energy. That's why it's quantized. And the blue line that you saw, oops, that's not blue. The blue line you saw represents the leap from an electron that was in the fifth energy level back down to the second. Now, of course, for it to get that far, it has to absorb a distinct, discrete amount of energy to get there. It's unstable, high energy, and it jumps back. And when it does so, it gives off a blue photon. You have to give off energy. And you should know, at this point, the blue photon has what? Shorter wavelengths, higher frequency. Its energy is high. The green, okay, let's get my green color, is a little longer wavelengths. So its energy is not as high. And the red is even longer wavelength. So its energy is the lowest. So the color theory that we looked at helps us decide, tells us something about the what? The electron transition. So the colors that we see in every part of our life is from electrons transitioning or transitions. From where? Well, if they're giving off light, it's because they're jumping back to the nucleus, to low energy ground state. Okay? Therefore, if you're going back to low energy, you must be losing your extra energy. Okay? So that is the Bohr model. Bohr was the first, and you can write this. He was the first. Okay, where am I? Oh, he was the first, and this would be number 4, to basically depict and understand all the spectralizing hydrogen. So he explained perfectly the bright, oh Christmas, the bright, big finger error, the bright line spectrum of hydrogen. So that red line, hydrogen, I can do this, hydrogen. He was the first to explain the bright line spectrum of hydrogen. As what? As transitions perfectly. Okay? And the energies that he measured were the exact energies electrons jumping. And from this point forward, we had a better understanding of what these bright line spectrums were. So this is the Bohr model, a planetary model based on the ideas that were quantized. He was first, I guess, the bottom line, he was the first to do what? He was the first to quantize the atom, describe the atom in discrete energy levels. And he did it with electrons, and he was right. Okay? He was the first to describe how the atom has different energy levels and discrete. And again, it's from the organization of electrons. And electrons based on proximity. Closer you are, the less energy you have because the nucleus is controlling you with its positive force. The farther you are, the higher the energy. Okay, let's go on to the homework and let me see if I can help you with that. There are two worksheets that you're responsible for. Here's the first one. What was the first model of the atom that organized electrons outside the nucleus in a way that reflects the planetary model? Well, if your short-term memory is not working too well, it's Niels Bohr's model of the atom. Okay, it's what we just talked about. All right. What does quanta or quantized mean? Very simply, it means what? A specific amount of energy. Okay? Nothing in between. The atom is quantized based on the arrangement of electrons. Who was the first to create a model of the atom that quantized the atom? Okay, well, first to create a model of the atom, so that would be Niels Bohr again. Okay, he quantized the atom through what? The arrangement of electrons that went in circular orbits around the positive nucleus. Okay, which scientist first described that matter is quantized? Well, Max Planck was probably the one who did that, who was working with black body radiators and so that light, okay, well, we'll just leave it at that. Max Planck was the first to see that there were oscillators, something like the atoms had oscillators that could only absorb and emit discrete amounts of light, okay? Which science proved that light is both a wave and a particle? Well, that would be Einstein's theory, that he found that in the photoelectric effect, which I kind of use the glow-in-the-dark material, that demonstration to help you with that. But he found that light travels in these packets called photons, and light has particle behavior. Okay, so the light travels in packets, not as a continuous wave. All right, what do we call a light that acts as a particle? That's called a photon. Notice we like to use the O-N ending. Okay, like a proton, electron. Why does blue light have more energy than red light? Well, energy is related to the frequency of light. So blue light has a high frequency because its wavelengths are shorter. Okay, if you remember me with I was doing this demonstration with a slinky, and you can see that it takes a lot more energy to make a lot more waves. So blue has shorter wavelengths, higher frequency. So has shorter wavelengths, thus a higher frequency. A is the answer. What makes the atom quantized? It's the electrons in distinct orbits. Okay, that is the key here. Moving forward. Which orbit will have the highest energy? Okay, well, the farther you are away from the atom, the positive nucleus, the more energy you're going to have because you can exist farther. So we would say N equals 4 because it exists farther. It's based on proximity. It exists farther away. For those of you looking for the negative, there's less negative. It's not part of my course, but I don't want to confuse anyone here, so I'm leaving that out of my discussion. Which electron orbit has the lowest energy? Well, that'd be N equals 1 because it's closest to the nucleus. That means you feel the nucleus, in my case, Big Mama more. So you can't move because it's right on top of you. Draw an arrow on the diagram represents a quantum leap of an electron that releases energy. Well, several possibilities. If I'm releasing energy, I'm going from a what? A high energy orbit to a lower one. I'm going back toward the nucleus. So anything that goes back toward the nucleus is perfectly fine. As you can see, there's many, examples of that. So here we go. If an electron becomes excited, it just absorbs energy to become excited. If electron is unstable, it just absorbed energy, right? To get unstable, you have to jump farther away. If an electron returns to its stable or original position we call ground state, the atom had to release the extra energy, right? Stable is low energy. If electron jumps to a higher energy level, it had to absorb energy to do that. If an electron returns to its ground state, that should be one word, The atom had to release its extra energy to jump back closer. The ground state is stable. Energy is released in the form of spectra, or you can say photons. All right, given the Bohr model, which electron jump require the most energy to be absorbed? That's key here. If you're absorbing energy, that means you're going farther away from the nucleus. And if you're absorbing the most, you need the most energy to pull away from the nucleus. That's why a 1 to 7 is the most energy to be absorbed. I'm going away. The next question wants the most energy to be released. That means I'm going from high energy to low energy. The most energy would be the biggest leap back. So 6 to 1 is the biggest leap back. It's the biggest jump backwards to the nucleus, to low energy. Which principal energy level, that's just the numbers of the shells, has the highest energy? 7, it's farther away. Lowest energy, 1, it's closer to the nucleus. Hopefully you're seeing a pattern here. When an atom does something, energies, when an atom, this is the whole story, when an atom absorbs energy, I'm going to use this, absorbs energy, electrons from a lower energy level that are stable make a quantum leap to higher energy levels that are unstable. When the atom jumps to a higher energy level, the atom is said to be in an excited state and very unstable. Electron then emits energy in the form of light or photons and returns to its stable ground state. Okay, let's go on to the next worksheet. Okay, in this worksheet we have bright line spectra. Now, of course, we don't have colors, we just have lines, but these represent some color line. Okay, now this thing right here is wavelength, is the size of the wave. Okay, and these are the numbers of how long these waves are. So what we have is we have 3 elements: lithium, cadmium, and strontium. These are their individual bright line spectrums that we get from exciting them and letting them jump back. They're the footprint of all elements. Elements all have a unique spectrum because they have a unique arrangement of protons and electrons. This is a mixture of some of the elements, and we put them through the spectrum again. So going through the question, number 1, which elements are in the mixture? Well, if I look at the mixture's bright line spectrum, it's got a bright line spectrum a little above 700. The only one that has one like that is strontium. If you notice, strontium lines are found in the mixture. So it must mean that I'm made up of, guess what? Strontium, definitely. Now, who else is in here? Well, I can see that also cadmium. Oh, not cadmium, because if it was cadmium, cadmium had this line here. So it's not cadmium. It's what? It's lithium. Lithium's lines are found exactly on the mixture. Whereas what? Cadmium lines are not found. So it's going to be, the mixture is made up of lithium, okay, and strontium. Those lines individually for lithium and strontium are found in the mixture. And that's how we can actually, that's how they actually found the sun, as the same thing we keep talking about. So that's D. Okay, moving forward. What is the correct relationship between wavelength of energy and each bright line? Well, the longer, like I said, the wavelength, the lower the energy. So A doesn't work out. Okay, shorter the wavelength, the lower the energy. Yes, when the wavelength is smaller, that means they're happening a lot more per second. It takes a lot more energy to do that. So the different colors are based upon different size of wavelengths. So B is the answer. Which bright lines in its spectrum have the highest energy? Which element has bright lines from electron transitions that we just learned about that have the highest energy? Well, high energy means short wavelengths. So if I look at my chart here, let's clean this up. The size of the wavelengths are given below. Okay, and I can see that the shorter wavelengths, right, would have the higher energy. So the question is, which element has bright lines that have the highest energy? Okay, well then it would have to be strontium. None of the other two have lines in this shortest region. So strontium has the highest energy. Given the following colors of light in order from lowest to highest energy, Roy G. Biv, right? Red, orange, yellow, green. I'm just spelling out the mnemonic for these colors. What color would the approximate light for strontium at 410 be? Well, 410 is a pretty small wavelength compared to the other ones that are bigger. So I'm guessing this one would have to be with the highest energy. And we learned the highest energy, Roy G. Biv, would be violet. So you can guess violet. Right? Reds have the longest wavelength. And as you go from reds to the other ones, the what? The wavelengths get smaller. What is the approximate wavelength of the electron emission of lithium that represents the greatest leap? The greatest leap back to its ground state would be an emission of the shortest wavelength with the highest energy, the longest leap. So I'm looking for the highest energy for lithium, which would mean the shortest wavelength. So I would say about 460 or so. I'm guessing it's an approximation. That's why that's the answer. Next question, what is the approximate wavelength of an electron absorption? That means you're doing what? You're going away from the nucleus, away from its ground state. Well, that's a trick question. None of the choices are correct because if you notice, this is a bright line spectrum from emission, although I probably should have written that there. These are emission bright line spectrums. Absorption bright line spectrums are when you have a full spectrum missing some of them. So these are only given off when electrons are jumping back toward the nucleus. All right, so that's why that's not there. Going on to the back page. Okay. Given this information, which is the red line jumping back, please draw the 4 energy transitions. Well, 3 going back to 2 gives off the red line. So if this is 1, let's just do it this way. This is 1, 2, 3, 4, and 5. The red line, as I have been drawing many times, goes from the 3 back to the 2. Boom, there's the arrow. Okay, and that's the red line. The green line, felt like I've done this before, okay, is the 4 back to the 2. And the blue line is from the 5 back to the 2. And I guess I should make my 4 a bigger arrow, bigger, thicker arrow to show it's more energy. Well, the distance also. And then the, I guess the violet line, which I don't have for a line here, is the 6th going back. So I need to add one, a circle. So this would be 6th energy shell, and that would be violet. I don't know if you have it violet. Okay, so let's pretend that magenta is violet. I'd be going from 6 back to 2. Longer the leap, the greater the energy. How do I get here? Energy had to be absorbed. Okay, I guess this is the nucleus. All right, hope that helped.